In this video, I want to talk about threaded features being used as datum features and being controlled with tolerances of position. So I'm going to quote from ASME Y14.5-2018, page 38, section 510. Unless otherwise specified, each tolerance of orientation or position and each datum reference specified for a screw thread applies to the pitch cylinder axis. So that is the default requirement, the pitch cylinder axis. Now, what exactly does that mean? Well, the short story is you can't simulate that the same way you would simulate a cylinder. So if we have an internal thread, so a threaded hole, we cannot use a gauge pen to simulate the axis of the thread. What we're simulating is the axis of the minor diameter of the thread. And I'll get to why that's not the end of the world or anything. I want to make you aware that as far as Y14.5 goes, unless you override that, you need to be looking for the pitch cylinder. Now for standard threads, it's not a big deal. They make, and in the later part of this video I'll show on the plate, they make special gauges for this that thread in, and they're meant to locate that pitch cylinder, and they've got a precision pin on the end so you can find that. Now with datum features, a similar thing happens. Say we have an external thread, so a simple part, the thread is going to locate this cylinder for whatever reason. We're going to identify the thread as datum A, and we're going to use it as a primary datum reference. Now in this case, this would be rather difficult to simulate without special custom equipment. If there is off-the-shelf equipment, please let me know. I'm just not aware of it. What I think most people would do is say, well, we'll just grab this in a collet or a chuck, or put it in a V-block, right? Just like you would if it was a cylinder, and you can spin it, right, and check for this, right? They work the same way for runout. In order to find the pitch cylinder of this, we cannot rely on the major diameter, right, the pointy part of the threads. We have to have some tool or some machine to find out what the actual pitch cylinder is. Now in a little bit, I'll show the difference graphically, and again, I'll show it on a surface plate actually measuring it. For now, I want to quote the second part of this section 5.10, page 38. When an exception to this practice is necessary, the specific feature of the screw thread, such as minor diameter or major diameter, shall be stated beneath or adjacent to the feature control frame or beneath or adjacent to the datum feature symbol as applicable. So we don't have to use the pitch cylinder. As I've explained just a little bit, that can be somewhat complicated. We can override that requirement and indicate that this thread and this thread can be simulated just like it was a cylinder. We're just relying on either the minor diameter or the major diameter. In either case, the way it gets reversed, right, we use the major diameter here. That's the tippy tops of the threads. The minor diameter of an external thread is the root, right? And that's just much more difficult to capture. Inverse for an internal thread, the minor diameter is the part you can actually kind of touch with your finger. The other part is inside of the part, again, the root of the thread. So, just like I quoted a minute ago, for an external feature, adjacent or beneath the datum feature symbol, and I've chose adjacent here, we'll say, I don't need to start, we'll just write major diameter. Now, normally I like to spell things out, so just write diameter, right? Letters are free on PDFs, basically. Y14.5 specifically indicates this as an example. So either way, in my opinion, is correct. Maybe this saves a little bit of room on the drawing. So this is telling us to treat this thread is essentially a cylinder, right? We've got the major diameter, we only need to consider that. So that now we can capture it in a collet just like we would a cylinder, capture it in a V-block just like we would a cylinder. It just makes it much, much easier to measure and verify. And again, this is a datum reference. On the feature we're controlling, right, not a datum reference, we'll put it under the feature control frame. So, as I said a minute ago, beneath or adjacent. So here we're beneath, we don't need a star. So it's indicating that we just need to find the axis of the minor diameter, the unrelated actual mating envelope of the minor diameter, which can, in the 1/4 inch, be accomplished with a gauge pen, just like measuring the axis of a plain hole. Much, much easier. But you need to specify this on the drawing. And you might ask, well, why is it the way it is, right? Why is the default so difficult? The reason is it's just engineering conservatism. There is a difference between the axis of the pitch cylinder and the axis of the minor or major diameter. The pitch cylinder will locate a mating part with a inverse screw thread. The minor or major diameter is just considering the tippy tops of the threads. So let me show you graphically what I mean. Okay, so I know this isn't the prettiest screw thread, but what I want to get across here is it's clearly oriented wrong, right? We would want it to be perpendicular to this top or bottom surface. Now, if we found the axis of the pitch cylinder, it would look something like this. So if we took a threaded gauge in here, it would follow the actual pitch cylinder of the thread. Now, if right now we took a gauge pen and did the same thing, the gauge pen would be sitting inside of the minor diameter and the axes would be coincident. But there could be a situation where, and don't get on me on this. I know CNC machines make parts well. People say, well, I drilled the hole, I tapped the hole, right? This could never happen. If CNC machines always made everything perfect, there'd be no need to measure or inspect anything. So what we're looking here for are edge cases, right? Or especially in high risk industries. You wouldn't want somebody making, parts for airplanes saying, well, yeah, it's whatever, it's good. I know we drilled the hole, tapped the hole, minor diameter, pitch cylinder are coincident. This is why ASME goes to the pitch cylinder, because for whatever reason, if this happened where you, say, took a drill and re-drilled the minor diameter, the pitch cylinder does not change. If I thread something in here, right, it's going to follow the pitch cylinder. But if I took a gauge pen, and I know this is exaggerated, but I hope you can see what I'm trying to show you here. If I take a gauge pen, it's going to follow the minor diameter, which can be different than the pitch cylinder. So that's the reason pitch cylinder's default, right? It's always going to give us the true axis of the functional feature, whereas the minor diameter, easier to measure. And I would say most of the time is just fine, right? Using a gauge pen to measure a threaded hole. But just think of critical applications where, a tiny orientation error might be really bad, right? This is why we have a standard and, check things and inspect things. So that's it for this part of the video. I'm going to go to the surface plate and show you this in real life. In this part of the video, I'm going to show the difference with simulating our pitch cylinder versus our minor diameter. When we simulate our minor diameter, we can use a common gauge pen and treat it just like we would a hole. To simulate the pitch cylinder, we need a special gauge, right? This is used to locate threads, so this threads in, and it's got a pin so we can tell where the axis of the pitch cylinder is. Now it's not perfect, right? Ideally this would be the full length of the thread, but that's what I have on hand. Right? So this would thread in here, So this would thread in here, then we'll touch it with our height gauge. Now, to simplify, I know the X direction of this part is good. That's the way I made it. We're only gonna check the Y direction. I did a version of this video where I did everything and it took forever and it really didn't help anything. So we're set up to measure from datum C. So why don't we start with our gauge pen. I'm going to touch the table, get 0. So our gauge pen gives us 2.2280. I'll show you the write-up toward the end here. I'm going to move this off. We're going to check the same spot with our thread locator. Notice the thread locator has a different diameter, right? It's going to be 1/4 inch. And we'll discuss, taking those into account in a little bit. I just want to show you how the actual measurement takes place. I'm just looking for the highest point on our pin here to make sure I'm measuring it where I'm supposed to be. 2.1190. But right now the numbers aren't super useful because we're comparing a gauge pin with a diameter of 0.424, and then this thread locator has a diameter of 0.25. So we're not off by 100 thousandths or whatever it looks like now. It'll be less than that. Okay. Now we've got to check the other side of the part, right, to get the orientation error accounted for. This is going to be a little bit trickier. I don't have a great way to do it. What I'm going to do is move the part up like this so that I can check this side, right? Now, I can't just clamp it here, right? Because I need to know this distance. I've got to take that into account because we're measuring from a datum. So, and this is not perfect by any means, but it'll work. I'll create a stack of precision, flat things. So 1, 2, 3 block and some gauge blocks. And that will get me above here, and it's going to clear this. Okay. Now, you might say, well, isn't there tolerance stack up here? And you'd be correct, there is, but keep in mind, these all have very, very small in the tenths of thousandths of tolerances. So for our demonstration here, it's not going to be a big deal. Okay, now I needed those gauge blocks so I can get a 0 off of that. Right, the blocks are just kind of an extension of our datum simulator. Going back up. So we're all set up. We did this side already, which I've called the near side. I'm going to spin around and get what I call the far side. And I call it the far side because it's normally the one that's kind of out of our reach because it's contacting our simulator. Lower down on here. Make sure we're at the top of that gauge pin, 2.2000. Now we'll do the same thing with our thread gauge. We got 2.1235. Okay, so our results here, I know it's a lot to look at. Here's the basic part with the X and Y directions at the top here. We've got our gauge pin diameter, right, 0.424. Radius is 0.212, or half the diameter. Thread gauge, the pin we were measuring with, is a diameter of 1/4 inch, so half of that is 0.125. Like I said, the X I just zeroed out, right, for simplicity here. The Y, right, there is an error. So we've got Y near and Y far, the far side being the datum side. With our gauge pen, we get two different readings, so we know there's some kind of error there. And then we've got our thread gauge side, right, again, near and far, much less of an error. So in this case, the minor diameter is kind of lying to us. It's way off, but the pitch cylinder is good. Quick calculations here. We take the worst of the readings, the one that's furthest away from the true position. So with the gauge pen, it was plus 16 thousandths. Gives us a diameter tolerance zone consumed of 32 thousandths. The thread gauge gave us a worst of negative 6 thousandths from the true position for a diameter tolerance zone consumed of 12 thousandths. And this is assuming that the X is perfect, right? X is 0. And I think that's the way I like to do this now. It just simplifies things. What we're seeing here on the board, I showed a similar thing, right? But now you can see in real life, this can happen. Now you might say, well, this is a 3D printed thread. How could this happen in real life? And you might be right. I mean, it is a difficult thing to do, but it is possible. And really the point of this video was just explaining why the pitch cylinder is the default. It's the true measure of what is going to happen when you thread something in there, whereas the minor diameter is not. The minor diameter can be very useful for measurement purposes. It's much easier to use a gauge pen, but you cannot assume that. It's got to be stated on the drawing, which is very easy to do. And I recommend if your design allows it, go for it. For non-critical situations, it would be good for a lot of things, much quicker to measure. So that's the end of this video. If you enjoyed it, please like and subscribe and leave a comment down below.